Okay, that's the most bizarre thing I've ever heard.
Really?
Yeah.
I've said
He said so much bizarre stuff in his class, and that's the most bizarre.
that's the one that tops it.
We talked about a guy killing a chicken and healing a baby at the same time, and that's more bizarre.
Yeah, but no, but it was cool. I mean, this is just random.
I mean, man, come on.
Okay, anyway.
If he turns
Are
his
we
head too
going?
far, he'll just cut his face. Yeah, we're going.
I wonder what people watch. They just randomly watch. It's like, what's this about?
I'm subscribed.
Skin defeather a chicken in 14 seconds.
Can we watch
I'll
that?
sit in my English group chat.
What? I'm interested.
An English group chat as
Yeah.
opposed to like a Russian group chat.
Yeah.
I got one of those.
Oh, English
Yeah,
class.
English class.
Okay, that's why I was confused. I didn't know if it was like the country,
Here's
the
the
class,
Quizlet
the
for vocab.
language, you know.
Russian group chat.
Okay, I want to see this video.
Okay,
No, it's like a 5-gallon bucket, and they kind of like put some stuff, and they just spin it. And
Well, I mean, is it like that one thing, you know, when you can... You just like put the whole thing in.
And stay in 14 seconds.
It's gone.
all right. Any questions on the net forces assignment?
Lots of them.
Huh?
No.
Not?
9.
Whoa, whoa, whoa. Vaughn is going. No, I have a question.
3 and 4 and 6.
Whoa.
1 through 11, please.
Wait, 4 in conjunction with 6.
5, 6, and 7?
No.
Okay. Yeah. Trust me, Vonda. That's how we want to play this question. Okay. So, and here's my frustration for some of you that have come up and asked for help. What's the first thing that you have to do? Draw a picture. Now, here's the deal. At most, you're going to have 4 forces. At most, like with this box situation. So anytime you have something sitting on Mother Earth, what are you going to have? What are the 2 forces you're always going to have?
Your force gravity?
Yeah, gravity pulling down, right? And your normal force acting upward, okay? You can always start with those 2, okay? You can... What is wrong with this? I've lost my pen.
lost my pen.
So look,
Oh, wow.
Boom. Oh.
Whoa.
Whoa. Oh.
I'm gonna hide behind it.
okay,
Sorry, bud.
so... Typical Katie.
Brick wall.
Okay,
We're still winning.
all right. So, don't make this overcomplicated. If you have a situation like this, at least always find the way to the option. Okay, take mass times gravitational acceleration. Get the number and then decide if you want to make it negative. Okay, which in this case it's going to make sense to make it negative because that's acting downward. Your normal force, unless you're on an inclined plane, your normal force is just the opposite of that. Okay, that's it. Don't make it complicated. So, has somebody found the weight of the, what is it, 1.5 kilogram box? 1.5? Yeah, which is like, what, 14.7, okay? So this is negative 14.7 newtons. So what's your normal force? 14.7. Don't make this difficult. Now, horizontally, at most, you're going to have 2 other forces. You can have a force applied, and as long as it's moving, unless you're told that it's a friction of the surface, what are you going to have in opposition to it? Your force friction, right? Okay? Now, if you look on number 4, all I'm telling you is that an 18 Newton force is applied to a 1.5 kilogram box. Did I give you any information at all about friction? No. So, number 4 is the easiest problem on the entire assignment. You set FAP plus FOP equals FNET. You have your FAP, which is 18 newtons. I gave you no information about the opposing force. Take 18 newtons and divide it by the mass. You're going to get an acceleration of 12 meters per second squared. Okay, it's the easiest problem on the entire assignment. Do not screw up number 4. Now, 5, friction rate rears its ugly head. Okay, now how do you know there's friction involved in number 5? I gave you mu. Oh, right. Oh, Bergkamp turns into a jerk again. So you go, oh, mu equals force friction over force normal. So you can find your force friction because now you know your normal force, which is 14.7. But here's where you're going to have to, dare I say, think just a little bit. Okay? Yes, I said the T word. So look, what's going to be the sign of your frictional force, positive or negative? Negative, because that's going to be working in the opposite direction of this 18 newtons. So you're going to take mu times your force normal, you're going to get your force friction. Now, to make this box move and accelerate, is your frictional force, before you even do your calculation, is your frictional force going to be bigger or smaller than 18 newtons? Smaller, because if your frictional force was, say, 25 newtons, and you only apply 18 newtons of force, what's going to happen? It's not going to move. Okay, it's not going to move, right? So if I take, this 1 kilogram mass, and I apply a force to it, okay, I'm pushing on it, but it's not moving because the force that I'm applying is less than the frictional force to overcome that frictional force. Now, if I apply enough force, wow, then I can make it accelerate. So just because you apply a force doesn't mean that you're going to have an acceleration, which is why you all are sitting in the chair and not accelerating, because the normal force is balancing out. So, look at this in terms of a chart. And I cannot emphasize this enough, the importance of this chart. FAP, FOP, FNET. Okay? You have to set up this chart. Oh, my applied force. That's 18 newtons. You're going to find the frictional force by taking mu times force normal, and the difference between those two is your net force. So your answer to number 6 should be around 10. Okay?
Yes.
Yes? You like that?
How many secrets are on number 6?
Well, everything you have is like 3. Okay? But
When you subtract.
yeah, so you should end up to the hundredths place because you're subtracting. Yeah, you should technically end up to the hundredths place. So now, your answer to number 7. Should your answer to number 7 be bigger or smaller than your answer to number 4? Shively, what's this? Is this like a Zen thing? Okay, does that help?
Wait, this does help. I do it up here though.
Really?
Yeah.
Okay.
Sometimes I do it really fast. Yeah, 'cause I like the noise.
Elon Musk. Ooh, sharp jawline. Okay.
Dude, don't cut yourself.
I'm just jealous. Maybe that's it. I used to have a sharp jawline.
My answer is it needs to be smaller.
Okay. Why does it need to be smaller?
Because that's what my math said.
Because we
But
have
why?
friction.
Why? That's right, there's friction. You're still applying the same
Elon Musk.
force, but now friction is working against you. So now you have to pay off the gravity mafia. So your answer to number 7 should be around 7. Okay, that's an ish. Okay,
Okay, a big issue.
it's big-ish. Okay, but your answer to number 7 should be around 7. Now, so let's talk about number 8. On number 8, when something's going vertical, the rocket, vertical calculations are simpler. Why are the vertical calculations simpler? Because what are the only 2 forces you're going to have vertically at most?
Gravity.
Yeah. Gravity trying to keep it down. No, not your normal force. Once it's up in the air,
Yeah.
you can have some force applied from the rocket engine. You don't have to worry about friction. Okay? You don't have to worry about your applied force. It's just this is it. Okay? Now, if this thing is going to get off the launch pad, what do you know about that applied force?
It's got to be bigger than your force gravity.
Yeah, because if it's not going to happen. Okay? It's like Mary, bless her heart, she goes down and she grabs a hold of, 500 pounds on the barbells. Okay? Bless her heart. She can lift with all her strength. She's probably not going to lift 500 pounds. But once she tries to lift it, what's good? Let's say that you have like scales underneath the 500 pounds. When Mary tries to lift it though, even though she can't lift it completely up, what's going to happen to the reading on the scales?
It's gonna go down.
It'll go down a little bit because she's providing some upward force. Now, I might be completely wrong. Maybe you were just intensely, okay? Yeah, okay? We'll bump it to 1,000 just to be sure. Okay, so she can apply an upward force, but she's not going to accelerate that weight up off the ground. So if you're going to get this thing off the ground, you have to apply a force that's greater than the weight of the rocket. If you don't, it's not going to go anywhere. So I promise you, there's going to be a question like number 8 on the test. And it's going to be on the bottom of the front page. I'm going to tell you exactly where it's going to be. And here's what you're going to do wrong. You're going to see 129 newtons, and you're going to divide that by the mass, and you're going to get an acceleration, and you're done. Okay? And you're not going to pay the gravity mafia. Okay? What's the only time you don't have to pay the gravity mafia?
You're in deep, deep space.
And unless I explicitly tell you you're in deep, deep, deep space, you have to pay the gravity mafia. Okay? You have to pay them. So if all goes well on number 8D, you should get an answer around 200 meters per second. Okay? Go with this. All right. Now, make sure on that vector diagram, notice on the vector diagrams, I said just make a sketch. It doesn't have to be to scale, but here's what I want. I want the force diagrams, I want some velocity diagrams, and an acceleration diagram. Make sure that your acceleration vector is pointing in the same direction as your net force. Okay, don't tell me the net force is pointing up and your acceleration vector points down. Not cool, okay? It's a violation of pretty much every tenet of physics. When you get to 8E on the backside, there's 2 distinct diagrams that I want, and label them clearly. What's happening on the way up is that rocket is approaching its maximum height, and then what's happening on the way down once it starts to fall. So here's what I want to clearly see. I don't want random arrows. I want to clearly see the velocity vectors. Are they getting bigger or smaller? Label them like V1, V2. I want to see an acceleration vector, and I want to see a net force vector. So there should be 3 sets of vectors for each one. A velocity and acceleration and force on the way up, a velocity and acceleration and a force on the way down. Okay? Make sure on H that you label everything. So your diagram on H, keep in mind this is a velocity time graph, not a position time graph. On H, this is what your diagram should look like. Now, if your numbers don't fit on this on the number scale for this velocity time graph, don't go, oh, Burkamp screwed up. He didn't give us enough space. No, trust me, something went wrong. So, if your numbers don't fit within this, it's been a train wreck. Okay? And also, on that graph, go through and make sure that you label everything that I want labeled. Okay? Make sure that you label everything on the net force, the acceleration, max height, engine shutoff, that type of thing. Okay? Are we good, Vonda? Yes.
Can we talk about number 11?
We can talk about number 11. Okay. Well, let's look at this. Okay? So if you go to the rocket, right? What's the downward force acting on the rocket?
FG.
How much? What's the numeric value? What do you have as the numeric value of the gravitational force acting on the rocket?
What number is this?
Number 8. It's like 5, I think it's like negative 49.
Oh, yeah, negative 49. Yeah.
Okay, so here's the deal. So here's my question. Does the net force have to be negative 40, or excuse me, does the net force have to be 49 newtons or greater to get this thing off the launch pad? That's
No.
the fundamental question.
No.
What has to be greater than negative 49?
That.
Yeah. The only thing that has to happen is that I have to have a positive net force. Okay? So this, my net force doesn't have to be greater than negative 49, but my applied force does. Okay? So don't get those two confused.
That's what I wrote.
Yeah. What's the only time in a rocket problem your applied force is the same as your net force? Yeah, when there's no gravity. Okay, that's the only time. What's the only time the weight of the ship is the net force?
When it's
And there's what? What's the only time your net force is your gravitational force?
when there's no applied force.
Yeah, when it's up, when it's in
When
the
the
state of free
engine's
fall.
off.
Huh?
When the engine
When
is
the
off.
engine is off. That's it. Okay, Bonder, are we good? Okay. Make sure on number 5 that you have labeled every vector, okay? Basically, one should look like a square and the other one should look like a cross, okay? Make sure that you have labeled every vector. If there's a net force, make sure that you draw the net force and tell me the numeric value of it. Make sure that I see the scale, okay? Make sure that I know which direction the forces are pointing, and make sure that you have used a ruler to draw them to a particular scale. Mr. Edward, did you hear that?
I did.
Okay. All right. Anything else? Going once, going twice? So, there are 2 things I didn't do in Peace Corps.
She dropped her. She
I didn't wear Birkenstocks, and I never smoked weed. Which is
Not in the Peace Corps.
or ever.
Why don't you reverse the honestly comfortable?
Okay, no, you honestly look like a hippie beating it, okay?
Oh, you look like a hippie beatnik.
I mean, they're
No,
just samples.
no. They would take
I mean,
away.
that would be weird to
No,
have
no,
your toes
no.
out.
No, can you imagine if I walked in wearing like,
With your toes out.
yeah.
I feel like you relax a little bit.
Yeah, I have.
Have you ever gotten a
I
pedicure?
am, I'm broke with you.
Hey, have you ever gotten a pedicure?
Huh?
Have you ever gotten a pedicure? Eli gets
what's-
pedicures.
Pedicures are nice.
Eli gets pedicures.
What's your gut feeling?
Eli also
We've known
wears his
each other
toes
since
out.
you
No.
were freshman.
Yeah,
But
I'm gonna call that one a
They're
hard
really
yes.
I
good
said
for
Eli
you.
also wears
Okay,
his
no,
toes
that's
out.
not the question.
Eli keeps the toes.
What's your
No,
gut,
you have
what's
not.
your gut
Yes.
feeling if
I
I
need
didn't
to
have a
show them
pedicure?
bad.
No,
Keep them
but I,
toes
Okay,
out.
that, okay. End of
So you
discussion.
get pedicures and wear Birks
and smoke weed.
on the weekends.
No. Not in the no, but God, no. Okay, so,
What a nerd, am I right?
the lab, we're actually gonna start this lab today, we'll finish it up tomorrow. But first we gotta watch a couple videos on the,
Yes. Sorry.
You should make her start the lab without watching the videos.
on the space shuttle launch, okay? This is back when, and it also talks about the Apollo 5, or the Apollo mission. So sit back, we'll watch a couple videos, and then we'll chit chat.
There's 7 seconds at the start of this race and 2 things I've never done in Peace Corps. And it's zoomed out of this. Dang, Eli, why do you have so much gum?
It's like a dollar or something. It's like a dollar, like Walmart.
Dude, all this gum and you won't give me a piece?
I literally just hopped into this.
Yeah, well, you took forever to follow me back on Twitter. So.
What?
think
I still did
think
it.
I did
I'll follow you on
I
Twitter.
did follow you back when I followed you. Matthew.
Yeah, why would I follow you on Twitter?
English together.
It doesn't mean anything. It means nothing.
How do you decide who to follow back?
Matthew, don't deny
If
it.
I want to see their tweets.
Okay,
Accomplishments in spaceflight have proven to be some of man's most triumphant achievements. The underlying principles which made these achievements possible came as a result of hundreds of years of investigation into the behavior and structure of matter. It's these principles of physics which play the foundational role in making spaceflight a reality. The launching of a rocket provides a spectacular display of force and energy. From a physics viewpoint, a rocket launch vehicle can be thought of as a large force machine. Its sole purpose is to apply a continual thrusting force in order to produce an acceleration. If the rocket is to achieve a low Earth orbit, the magnitude of the acceleration which is required tends to be quite large. The rocket must go from a state of being at rest on the Earth's surface to that of traveling 8,000 meters per
And
second
later on, you
at
see
some
the
given distance
significance
above
of
the
that
Earth.
8,000 meters per second. It has to do with
This
the
tremendous
temperature.
velocity change takes place over a relatively short period of time and necessitates the large amount of energy and acceleration provided by a rocket launch vehicle. The single most important
So that
component of a
these are
launch
the
vehicle
Saturn
is the
V
rocket
rockets
engine.
that got us to the moon.
Use
So
of a
that-
rocket engine
that gives you
provides the
some
means by which
perspective on
thrust is
scale of
produced
how
in the
big
vacuum
those
of
are.
space. Since oxygen is not present in the space environment, an oxidizer must be carried on board the rocket along with the fuel. The Space Shuttle's propulsion system is made up of 5 different rocket engines, 3 main engines which use liquid propellant, and 2 rocket boosters which use a solid propellant. The tremendous temperature extremes which the Space Shuttle's liquid propellant main engines operate at required innovative engineering during their design. The engine's complex system of precision valves and pumps must handle the extremely cold propellants without freezing up. The liquid hydrogen fuel at minus 253 degrees Celsius is the second coldest liquid on Earth. However, when burned with liquid oxygen, the temperature in the engine's combustion chamber reaches 3,300 degrees Celsius, a temperature higher than the boiling point of iron.
Okay, so here's the engineering challenges that these rockets face. So you have liquid hydrogen, which is the second coldest liquid on Earth. Anybody know what the coldest liquid on Earth is? No? If hydrogen's the second coldest, how could hydrogen also be the coldest?
Nitrogen.
Yeah. On Earth.
John Hunter.
Get out of here, man.
Famous.
Let me give you a hint. It's one of the noble gases.
Said nitrogen.
Neon.
No, it's a noble gas.
Helium.
Helium, okay? Helium is the coldest liquid on Earth because the process, without going through a whole lesson in chemistry, basically you have to slow the molecules down enough where they stick, where they hit together and they stick, okay? And so it's extremely difficult to get the helium particles to stick together as a liquid. That's why you have to get it so cold. So the oxygen's relatively easy to make into a liquid because it's a bigger molecule. So in one situation, you have the second coldest liquid on Earth. Now, it burns, and then the gases coming out of there are hot enough not to just like melt iron, but actually to make it boil. So imagine that you're going to throw enough energy into like a chunk of iron, just not to melt it, but to completely make it boil. So all within the same system, you have to go from the second coldest all the way up to boiling iron. So that was a huge engineering challenge because, oh, okay, well, let's use iron. That's kind of a standard thing. Well, no, you really can't use iron because as soon as you light the engines, everything's going to boil off, okay? So that would be like trying to, build a house out of butter on a hot day. It's not going to work. So that, in and of itself, produced a huge challenge just dealing with the extremes of temperature. And also, what happens when things get really, really cold? What do they tend to do?
Break.
Well, they break, yeah. But do they shrink or expand? What do they do when they get cold? They break.
They shrink.
They shrink. But when things get hot, they expand. So at normal temperatures, everything might fit. So then you have to allow for that extreme. Okay, once you start putting that cold liquid through it, what's that going to do to the parts? Once that engine starts to fire and everything heats up, what's that going to do to your expansion? So there was a huge challenge just to build the engines to be able to handle those extreme temperatures.
In the combustion chamber of the rocket engine, the propellants are consumed in a combustion reaction. The thermal energy generated from the combustion heats the newly formed gases to extremely high temperatures. These gases, possessing a large quantity of kinetic energy, subsequently go through an expansion in the rocket nozzle and are ejected at extremely high velocities. With the fuel being composed of liquid hydrogen and liquid oxygen, the hot gas which is expelled from the engine is primarily water vapor. The thrust which is produced by the engine can be explained in terms of Newton's third law. As the engine applies a downward force on the gases, causing them to be ejected, The gases must also apply an equal and opposite
Notice that has
force,
nothing
pushing
to do
upward
with
on
the
the engine.
surface that it's pushing against.
This upward
It's all
force pushing
within
on
the
a rocket engine
itself.
is essentially a reaction force to the gases being pushed downward, and is responsible for giving the engine its upward thrust. Newton's second law of motion, expressed in terms of momentum, can be used to find the magnitude of the thrust produced by a single space shuttle main.
Now, this is where this is a little bit different than what you guys are used to seeing. You guys are used to seeing a constant mass multiplied by changing velocity over time. Okay, that's how you get, like, oh, here's the car, the mass is constant. With rocket engines, you change it up. You keep the velocity constant, but that's the velocity of the escaping gas. So that might be like 1,000 meters per second, whatever it is. The change in mass over time is how much fuel that thing consumes. Okay? So when you look at that, basically the more fuel that consumes per unit of time, and the faster that gas is ejected out of that nozzle, the more force that you're going to generate. But this is where it turns into like a catch-22 and it becomes a vicious cycle. You say, oh, we need more force. Okay, great idea. We need more force. But so you go, oh, we'll just build a bigger engine. What's the problem with building a bigger engine?
Bigger mass.
Yeah, you have more mass. The bigger engines weigh more. So if your bigger engine won't produce enough weight to make up for the bigger engine, there's no point in building the bigger engine. So this is where it becomes a vicious cycle. Oh, we need bigger engines. Well, guess what? Bigger engines weigh more. Guess what? To make the bigger engines work, that requires more fuel. Oh, great. Now we have to carry more fuel. So it's like you're going down into a rabbit's hole of this vicious cycle. Well, we need more engines. We need bigger engines. Well, those take more fuel. That's more weight. Oh, now we need a bigger engine. So that's the balancing act that you have to carry out.
Engine. With the propellant gases being ejected at a velocity of 3,600 meters per second and at a rate of 470 kilograms per second,
470
the
kilograms
resulting
per
thrust
second is about
generated
like
by
a
the
small
engine
car
is equal to
per second.
1.7 million
So
newtons.
each engine is basically
As seen by the
taking out
second
a small
law, the
car
greater
per
the rate
second.
at which the hot gases are exhausted and the greater their velocity, the greater the resulting thrust will also be. Solid propellant engines make up a second group of rocket engines. These engines are much simpler in design due to the fact that they require no pumps, valves, or complex propellant feed systems. However, once ignited, they cannot be shut down.
Yeah, that's a key thing.
The
Once
shuttle's
you
solid
light them,
rocket boosters
you
use a
can't turn them
propellant
off.
which consists of aluminum powder as the fuel and ammonium perchlorate as the oxidizer. A rubber-based polymer binder is also added. This mixture fills the entire length of the solid rocket motor, except for a hollow channel extending through its center, which serves as a combustion chamber. When ignited, the propellant burns from
Don't
the
stand
center
behind
out
that.
towards the sides of the casing at a nearly constant rate. An extraordinary amount of thrust is created. Propellant gases are exhausted at a velocity of 3,300 meters per second and at a rate of 4,000 kilograms per second, creating 13 million newtons of thrust. Enough thrust to maintain the flight of 20 747 airliners. The Space Shuttle system is the most technologically advanced and complex machine on planet Earth.
But built by
Unlike the Saturn
lowest
V
bid.
rocket, which carried its payload to the moon, the shuttle is designed to attain a low Earth orbit. Achieving the necessary orbital velocity is no small task, as it requires the combined thrust of the shuttle's 3 main engines and 2 solid rocket boosters. With the large external tank storing the liquid propellant used by the main engines, and the 2 solid rocket boosters containing their own solid propellant, the total mass of propellant aboard the shuttle equals an enormous 1.7 million kilograms.
That's just the fuel.
This propellant mass accounts for 85% of the shuttle's total
So
launch
this
mass
is basically a
and
flying
provides
fuel
20
tank.
billion kilojoules of chemical energy, which is necessary for attaining orbit. The filling of the liquid oxygen and liquid hydrogen tanks occurs on the launch pad several hours before launch. The oxygen vent arm, which caps the top of the external tank, allows vaporized oxygen to escape from the tank, and thus prevents the tank pressure from building up to excessive levels. A similar arm allows the lower positioned hydrogen tank to also be vented. As the final countdown begins, the flight crew is taken to the launch
Check
site
out
and
the guy on the
enters the
right.
orbiter by way
Has
of
to
an
be an NASCAR
XSR.
fan. Look at the sideburns.
With all systems checking out in working order, the crew XSR is retracted at 7 minutes before launch.
Huh?
Stereotypical.
Yes, you're right.
3 minutes before liftoff, the main engines are swiveled to their proper launch
I'll tell you what
positions.
NASCAR stands for.
All of
later.
the shuttle's engines are mounted on a pivot device, or gimbal, which allows the flow of exhaust gases and the direction of thrust to be controlled during ascent. The oxygen and hydrogen vent arms retract at just 2 minutes before engine ignition.
Take that off before you try and fly.
At 7 seconds before launch, the sound suppression water system starts dumping 300,000 gallons of water onto the pad. This water is used to partially absorb the 170 decibels of acoustical energy given off by the engines, preventing it from fully reflecting off the pad and causing damage to the shuttle. Hydrogen igniters under the main engines are used to ensure that any hydrogen flowing out of the engines prior to ignition is burned off as it emerges. This prevents the buildup of a potentially hazardous cloud of explosive gas.
That would be bad.
At 6 seconds before liftoff, the 3 main engines are ignited. Shock waves coming out of the
Okay, so let's talk about this. We haven't ignited the solid rocket boosters yet. So why do you think they light those 3 engines first, before you light the solid rocket boosters?
Because you can't turn off the solid
Huh?
ones. You can't turn off the solid ones.
Yeah, you can't turn off the solid rocket boosters. If only 2 of those start, of the 3, you can shut down the other ones, okay? If they're not going. So you fire those first just to make sure everything is cool. Now, you are putting out a tremendous amount of force at this point. But why can't the space shuttle take off at this point?
The opposing
it's not
force is
big.
greater. Or the net.
What'd you say, Madeline?
It's not bigger.
The
Then-
opposing
What's
force-
not heavier?
It's not heavier than the thought.
The applied force is not big.
It's not bigger than the mass.
So
It
the
doesn't,
force
it wouldn't
applied must
lift,
be
it wouldn't
greater than the
lift
force, gravity pushing down.
Yes.
Beautiful. Okay, you said you were right, but it was all
Wording.
wrong. Okay, so here's the deal. So if you were to take and pull the launch pad out from underneath this thing right now, even though the engines are firing, what would the space shuttle do?
Fall.
Would it fall at 9.8 meters per second squared? No, it's providing some force upward, right? But just not enough to overcome the gravitational pull. So you haven't paid enough into the gravity mafia yet. So the gravity mafia isn't going to let you go because of the fact that the upward force that you're supplying is less than the gravitational pull acting down. It looks cool, right? But it's not going to go anywhere.
throats of the nozzle, cause them to vibrate momentarily. At T-3 seconds, the main engines reach 90% thrust. 1/2 second before liftoff, the solid rocket boosters are ignited as explosive hold-down bolts are triggered.
Yeah, those kind of
During
happen.
the initial
too.
part of its ascent, the shuttle's engines deliver a combined power of over 100 billion joules per second, an amount of power which is equivalent to the output of 85 Hoover dams. A distinction can be made between the different types of engine propellant, as the main engines are observed to burn with a clean light blue flame as a result of the hydrogen and oxygen combustion. This contrasts with the solid rocket boosters, which burn with a bright orange flame due to the combustion of the solid aluminum fuel. The dynamics of the launch can be studied in more detail by examining the forces involved during the shuttle's ascent. With the 3 main engines ignited and applying their combined thrusting force of 5 million newtons, the shuttle still remains motionless. At this point, the upward thrusting force represents only a fraction of the total shuttle weight, which is equal to 20 million newtons. If the supportive launch pad was taken away during this period, the net force would cause the shuttle to accelerate downward. In order for the shuttle to accelerate
Look
upward,
out to the
the
right.
total thrusting force must be greater than the shuttle's weight. This takes place when the solid rocket boosters ignite. with the two solid rocket boosters applying an additional 26 million newtons of thrust. The total thrust from all engines is now 31 million newtons. At this point, the net force is directed upward and the shuttle lifts off. The initial upward acceleration can be determined by using Newton's second law of motion. With a net force of 11 million newtons acting on the total shuttle mass of...
Okay, so here's the heart and soul of what you have to understand out of this whole process. There's the absolute heart and soul. So, this is your applied force, okay? 3.1 times 10 to the 7 newtons, quite a bit of force. Your downward force is negative 2.10 to the 7. So the difference between these two values is that net force. So if I give you this problem, and I'm going to, and I'll say, hey, here's the force from the engines, here's the mass, find the acceleration. Here's what you're going to do wrong. You're going to take that force divided by the mass and say, there's your acceleration. You're not going to take the weight of the ship into account, okay? You have to take the weight of the ship into account to get this net force. Now, an interesting thing happens on the way to orbit. As this thing goes up, what's going to happen to the weight of the ship?
It's going to decrease.
It's going to go down. Why?
Because it's burning fuel.
Not so much that, it's going to be minuscule. There's going to be a much more obvious reasons why that weight is going to go down.
You're losing fuel and dropping
You're
pieces
burning
off.
fuel, right? You are burning a tremendous amount of fuel. You're burning about 2,500 kilograms per second, okay? So imagine 2,500 of these you're going through per second. Yeah, so here's the cool part though. Assuming that this remains constant, what's going to happen to the weight of the ship? It's going to go down because of the fact that the ship's going to weigh less. So what's that going to do to the net force?
Go up.
It's going to go up. Oh, now you can have a bigger net force. But not only do you have a bigger net force, what's happening to the mass that you're trying to accelerate? It's decreasing.
So your acceleration's going.
Whew. Yes. So your acceleration doesn't remain constant. Your acceleration actually becomes bigger. So if you were to look at an acceleration versus time graph, it starts at about 5.5, but it actually becomes a quadratic function because you're having a bigger net force that's continuously being divided by a smaller and smaller mass. So you have less and less stuff to accelerate. There's less and less inertia with a bigger and bigger net force. Your acceleration becomes bigger and bigger and bigger. So your acceleration doesn't remain constant. Your acceleration actually becomes bigger as well. Okay.
$2 million kilograms. The initial acceleration is equal to 5.5 meters per second squared. With the thrust initially remaining constant, the shuttle's acceleration will continually increase as the engines expel their propellant and reduce the mass and weight of the shuttle system. With 9,400 kilograms of propellant being exhausted every second, the shuttle's mass becomes reduced very quickly. After only 30 seconds into the flight, the shuttle is traveling with an instantaneous velocity of 200 meters per second.
So you're about 2/3
At
the
this
speed
point,
of
the
sound.
engines have already expelled 280,000 kilograms of propellant, reducing the shuttle's total mass and weight by 14%. Newton's second law of motion shows that the acceleration has now increased to 8.2 meters per second squared. At approximately 50 seconds into the flight, the shuttle enters a critical period during its ascent as its velocity approaches the speed of sound. As the shuttle moves through the atmosphere, it creates a disturbance in the surrounding air. The resulting pressure waves spread out in spherical shells at the speed of sound. As the shuttle approaches the speed of sound, it begins to catch up to the pressure waves it produces. With the distance between wave crests becoming successively smaller, the waves begin to pile up in front of the vehicle, creating a wall of high pressure. This pressure barrier, sometimes referred to as the sound barrier, presents resistance to the shuttle's motion. Breaking through this pressure barrier creates a period of maximum dynamic pressure and results in a considerable amount of aerodynamic stress being imposed on the shuttle. To minimize this stress, the shuttle throttles down in an effort to reduce its acceleration at the time of passage through the pressure barrier. After breaking through the barrier, the pressure becomes greatly reduced and the shuttle's motion is no longer impeded. With the shuttle no longer experiencing the high level of aerodynamic stress, its engines are throttled back up to 100%. Now, traveling faster than the speed of sound, the shuttle outruns the sound waves it produces. The resulting pattern of waves leads to constructive interference taking place, where successive wave fronts overlap, forming a single, very large wave front, which carries a tremendous amount of sound energy along with it. This large wave is called a shock wave and forms a conical shell of sharply increased pressure with the shuttle at its apex. Throughout the remaining atmospheric portion of its ascent, the shock wave will continue to trail behind the shuttle. After 100 seconds into the launch, the engines have expelled an enormous 940,000 kilograms of propellant, reducing the shuttle's total mass to almost half of what it was at the time of launch. With this decrease in mass and resulting increase in net force, the shuttle's acceleration has climbed to 18 meters per second squared. During this period of time, frictional heating caused by the atmosphere reaches its maximum level, as collisions with air molecules cause portions of the shuttle's exterior to reach temperatures of 1,000 degrees Celsius for a short time. At 2 minutes into the flight and at an altitude of 45 kilometers, the two solid rocket boosters have consumed nearly all their fuel and no longer provide thrust to the shuttle. At this point, the shuttle's weight can be considerably reduced by dropping the spent booster casings. The boosters are released by explosive bolts and are then powered outward and away from the shuttle by 4 small separation motors on each end of the solid rocket boosters. The reusable booster casings parachute back to Earth, splashing down in the ocean with an impact velocity of 18 meters per second. With the solid rocket boosters no longer present, the total amount of thrust acting on the shuttle dramatically drops. During the initial part of the vehicle's ascent, a large portion of the 31 million newtons of thrust was primarily used to accelerate the enormous mass of propellant on board the shuttle. With most of that propellant now consumed, and the shuttle's mass only 1/3 of what it was at the time of launch, the thrust provided by the 3 main engines is sufficient to maintain the vehicle's acceleration. At 8 minutes into the flight, the shuttle's velocity has increased to 7,000 meters per second, a velocity more than 20 times greater than the speed of sound. During this time, the acceleration approaches 30 meters per second squared,
So that
a
means
value which is 3 times greater than
you're
the
gonna feel 3
9.8 meter per
times
second
heavier
squared
than
gravitational
right now.
acceleration experienced at the Earth's surface. To the crew aboard the shuttle, the acceleration of 3 Gs forces them back into their seats as they feel the sensation of increased weight. Although the acceleration causes some discomfort and stress to the body, it is less than half of what was experienced by the Apollo astronauts aboard the Saturn V
So in other
rocket.
words, they're kind of rolling them under the bus, making them sound like wussies.
Cutoff of the main engines occurs at 8.5 minutes into the flight, at an altitude of 120 kilometers above the Earth's surface. 12 seconds after main engine cutoff, the near-empty external tank separates from the shuttle. At separation, a small valve in the nose section of the external tank is opened, allowing pressurized gas from the liquid oxygen tank
They
to
have to get
escape.
that to spin, because if they don't, it'll hit
The
the
escaping
atmosphere
gas
and
applies a
skip out
rotational torque to the
like a
tank,
rock
causing it
on-
to
like a
slowly
rock on
spin.
water.
This tumbling motion prevents aerodynamic skipping off the atmosphere and ensures the correct re-entry trajectory. As the tank breaks up upon re-entry, the debris will harmlessly impact within the pre-planned location in the Indian Ocean. With the external tank gone, the remaining orbiter represents only 5% of the shuttle's original launch mass. Having spent all of its main engine fuel, the shuttle's orbital maneuvering engines provide the final thrust for orbital insertion. The maneuvering engines, along with the other engines which are used while in orbit, use a hypergolic propellant. Hypergolic propellants are fuels and oxidizers which ignite spontaneously on contact with each other and require no ignition source.
But keep them
This
away
easy
from each
start
other.
and restart capability makes them reliable and advantageous for engines which are used a number of times while in orbit. At 10.5 minutes into the flight, the two orbital maneuvering engines fire to place the vehicle in a low elliptical orbit. The engines provide a total thrust of 53,000 newtons, giving the 95,000 kilogram orbiter an acceleration of 0.56 meters per second squared. The final step in achieving the desired orbit comes at 45 minutes into the flight, as the orbital maneuvering engines fire for a second time, placing the shuttle in a nearly circular orbit at 400 kilometers above the Earth's surface. Having attained an exceptionally large velocity of 7,700 meters per second, the shuttle is able to complete a full orbit around the Earth in only 1.5 hours.
Compared to the Earth, which spends 24 hours on its axis.
With no frictional forces present in space, the engines are no longer required to maintain the shuttle's velocity. Its constant motion will continue indefinitely without the expenditure of any additional energy. The shuttle's velocity is entirely maintained by its own inertia, as described by Newton's first law of motion.
Okay. Now, so the program that you're going to do actually deals with trying to land a ship on the moon.
Sending a manned spacecraft to another planetary body presents an enormous scientific challenge. That challenge is immeasurably escalated by having to also return the manned spacecraft safely to Earth. The extremely successful Apollo missions made a total of 6 different manned landings on the surface.
So what are the two big differences you're going to face trying to land on the moon versus landing on the Earth?
Bouncing.
Okay, I hate the word different.
Thing.
How is gravity going to be different on the moon?
Lower.
It's a lot less, right? That's one big thing. What's another thing that's going to be different?
There's no atmosphere.
There's no atmosphere, so you don't have to worry about drag like you do on the Earth. So like, don't try and fly on the moon. It's not going to end well, okay? Don't try and breathe on the moon. That's going to end worse, okay? So basically, if you throw a paper airplane on the moon, it's just going to go doink. Okay.
Surface of the moon. The lunar module, consisting of a lower descent stage and an upper ascent stage, allowed the astronauts to descend from lunar orbit and set down on the moon's surface.
That's what
This
you're gonna
vehicle was
deal
a
with
true
in those
spacecraft in
calculations.
that it was capable of operating only in the space environment. Having used its descent engine to land on the moon's surface, the lunar module would be required to do what had never been done before: lift off from a planetary body other than Earth. Due to the extremely different physical characteristics of the lunar environment, the dynamics of launching a spacecraft from the moon's surface greatly contrast the dynamics of an Earth launch. The black sky during the daytime bears witness to the fact that the moon possesses no atmosphere to scatter sunlight. Because of the lack of any atmosphere, aerodynamic stress and frictional drag are non-existent during a launch from the moon's surface. In contrast to Earth launches, streamlining of the spacecraft becomes unnecessary, as the lunar module's protruding components and non-streamlined configuration is of a functional design and presents no problems during launch. In order to provide the thrust required to lift off from the surface and attain lunar orbit, the ascent stage of the lunar module possessed a single rocket engine. Because there was no backup engine and no other means to lift off
Yeah,
from the moon's
there was
surface,
no
a
backup
malfunction
engine.
could
This is a
absolutely not
one-trick
be
pony.
tolerated. The single engine had to work. The engine used the most reliable propellants available, hydrazine and nitrogen tetroxide, 2 compounds which spontaneously ignite upon contact with each other. Because the gravitational acceleration of the surface of the moon is only 1.7 meters per second squared, the 5,000 kilogram ascent stage has a weight of only 8,500, a weight 6 times smaller than that which it would have had on the surface of the Earth. Because mass remains constant throughout the universe and is not affected by gravity, The spacecraft's 5,000 kilogram mass requires the same definite amount of net force to achieve.
Now, listen to this. This is one of those important things you have to understand. Net force equals mass times acceleration. So if you want that spaceship to have the same net force and the same acceleration on Earth as it does on the moon, all the calculations are the same. Because net force is mass times acceleration, and it isn't weight times acceleration. So if you want that ship to take off from the moon with, say, an acceleration of 5 meters per second squared, that's the exact same net force that's required on the Earth, because it's mass times acceleration. But what's going to be easier, in which situation is it going to be easier to achieve that acceleration? On the Earth or on the moon? On the moon. Why?
There's a low gravitational acceleration. So
Yeah, the Mafia isn't as strong on the moon as it is on the Earth. As a matter of fact, the Earth has a relatively strong gravitational field, which is why we have an atmosphere, because if we didn't, we wouldn't be having this discussion. Okay.
The given acceleration, regardless if it is launched from the moon or Earth. However, because the spacecraft's weight is reduced on the lunar surface, a smaller force can be applied by the ascent engine to produce the necessary net force. With the single engine producing a thrust of 16,000 newtons, a net force of 7,500 newtons is created. Applying the second law of motion shows that the resulting acceleration is equal to 1.5 meters per second squared.
So if you were to do that calculation on the Earth, it would be the exact same thing in terms of achieving that 1.5
Because of the
meters per
relatively
second
small
squared.
thrust required of the ascent engine in this comparatively weak gravitational field, the mass of propellant which is consumed is significantly reduced. Compared to the massive boosters required to put a spacecraft of similar size into Earth orbit, the mass of propellant aboard the lunar module is exceptionally small. The propellant, however, still makes up a significant portion of the lunar module's mass, and as it is expelled, the spacecraft's acceleration steadily increases. The command module, orbiting the moon at an altitude of 110 kilometers, is the vehicle which will be used to return the astronauts to Earth. Rendezvousing with this target requires the lunar module to be accelerated to the proper orbital velocity. At an altitude of 110 kilometers above the moon's surface, a spacecraft must possess a velocity of 1,600 meters per second if it is to remain in orbit. This velocity equals only 1/5 that which would be required to remain in orbit above the Earth at the same altitude. Having attained a velocity of 1,600 meters per second, the lunar module no longer needs to use its ascent engine, as it can make the necessary rendezvousing maneuvers using its 16 smaller reaction control thrusters. By having understood the physical characteristics of this distant world, the principles governing the launching of a spacecraft could be successfully adapted and carried out.
Now, the program you guys are going to use, so tomorrow, this is a program that I've got loaded up on the laptops, and the only way you guys can find it is to do a search, and I'll have it all up there, but it's called Interactive Physics 2000. And you're going to open up a file. This will be saved on jump drives, but you'll find Lunar Lander Modification for Burkamp. Now, so here's the program. This is what it should look like when you pull it up. Here's the anomaly about this program, is that when you hit reset, it will clear everything but your vertical velocity time graph. And the only way to reset that is if you click in that gray box and move it at all, it clears off that graph. Why it works that way, I have no idea. It has been that way since I got this program. It is the weirdest thing. Okay, so basically, it's kind of like a computer game. So if you wanted to go left, hit the left button. Now, here's the deal. If you wanted to go left, okay, which actual side engine is going to fire? The right side or the left side?
Right.
Right, because that's going to expel gas out to the right to make the ship go to the left. Okay. Now, here's the value of your main thruster. So basically, this is going to control the output from that engine. This is how you control it left and right. So let me hit run.
Get on the pad, Berg.
It's just like the helicopter.
Oh no.
Bring it around.
It's just like that helicopter.
Yeah, we're getting there. We're just toying with danger.
Oh.
Oh.
Whoa.
Yeah.
May I borrow Logan Brown?
Logan,
Yes, sir.
what class are you from? I'm gonna go and just go to your class.
Should we just all go in there and stand for a second
Okay,
and come back in?
so looking at this velocity time graph, how many direction changes were there?
Oh, I'm
What?
sorry.
3.
3?
Looks like it.
2?
Wait.
Oh, it looks like there were 3. It crosses 0 3 times.
This is the vertical velocity
Yeah.
time graph.
3.
There are 3.
Why, Honus?
Because it crosses this, like Max said, give Max credit. It crosses 0 3 times.
Yeah, because initially I had a positive velocity. Now, here's the question. Up there at the peak, is that a direction change?
No.
No, what's the only thing that changed sign at that point?
Acceleration.
The acceleration. Now think this through. Initially I had a positive acceleration, then I had a negative acceleration. Now this is the big idea. At the end of the day, net force equals mass times acceleration. Mass is always positive. So initially I had this positive net force, which is why that line was sloping upward here at the beginning. So if my acceleration is positive, guess what the sign of my net force is? Positive. Now, once I cross that peak and this line starts to come down, what becomes the sign of my net force?
Negative.
Negative. Because, and I know that because my acceleration also becomes
Negative.
Now here's the deal. How could I change the amount of net force? What did I fundamentally do to change the amount of net force? Because what does net force also equal besides mass times acceleration? Fat plus
Fall.
Fa. What's your opposing force?
Gravity.
Do you think I can change that?
No.
No. So to change the net force, I have to change the FAP, which is coming from the engine. So if you'll notice, and you can take this and like scroll back through this. So if I scroll back through, kind of do this one step at a time. So notice my value of my main thruster, that box to the right over here, notice that's staying at 9,000. So, but then I drop that thing to 8,300. Once I drop it to 8,300, notice that my acceleration becomes negative. So just because my acceleration becomes negative, does that mean the ship automatically starts to go down? No, it's still going up, and I know it's still going up because one of the things you'll see in this program, anything going up and to the right is defined as positive. Anything going to the left and down is negative. So what I've got here, I got an 8,300 Newton force that's going upward. I have a negative acceleration. So here's my question. Based upon that little bit of information, does this ship weigh more or less than 8,300 newtons?
More.
Why?
Because
You're
it goes
right.
down.
Why?
It slows down.
Because my acceleration is,
Less.
so my net force is,
More.
no. Is my net force positive or negative?
Negative.
Because, so I'm applying 8,300 newtons of force, but my net force is negative because I've got a negative acceleration. So this is like Mary trying to lift the 1,000 pounds. She's applying 999 pounds, but she hasn't quite, but we're only still end up with a negative acceleration if she lets go of it. Okay? So, now, but if I go back a little bit, Notice if I go to 8,400, what's the sign of my acceleration then? Positive. So if I have a positive acceleration, my net force has to be, so my applied force has to be bigger than the weight of the ship. Okay, so that's going to be the basic idea. So I know I've got a couple of direction changes because of the fact that that's when it's crossing through 0 meters per second. We're speeding up, slowing down. So if you hit reset, everything will clear off. Now, all these will go to 0, but the chart won't. But if you click on it and move it at all, that's how you clear it after each time. Why it works that way, I don't know. So, Mad Max, stop that for a second. Oh boy, Matt.
Thanks, guys. Thank
Had
you.
to step up and plate on that. Better take one for T. Doesn't take much, does it? Okay, so here's the deal. So up at the top of the page, I've got all of the parameters that you need. So the gravitational acceleration on the moon, negative 1.67 meters per second squared, 3 significant digits. You got the mass, 5,000 kilograms. How many significant digits? 3. See pattern forming here. Now, what we're going to assume is that the mass of the ship actually remains constant. In reality, it's going to change. If you were actually doing the calculations, that becomes a function of calculus in terms of, what rate are what rate are you kicking out per unit of time. So that's just going to get real ugly. So we're just going to assume that the mass is going to remain constant. So anything going up and right, whether it's displacement, force, acceleration, doesn't make any difference. Anything up and right is positive. Anything down and left is negative. Okay? So, just like you're not going to pull up to NASA and go, hey, let me take the space shuttle for a spin. No. Okay? You probably got to prove that you at least have some working knowledge of physics and Newton's laws of motion. Same thing is going to happen with me. I'm not going to turn you loose on those laptops with the program until you prove to me that, wow, I understand this concept of net force. So what I want done for tomorrow, and this is how tomorrow is going to play out, you're going to have page 1 and page 2 done. Then tomorrow, don't worry about page 3 and 4. That has to do with data from the program. You can't do page 3 and 4 if you try. So you're going to have page 1 and page 2 done. Then you're going to come up to me. I'm going to look through everything and make sure that everything is right. Then I will sign off on it. Then I'll give you the keys to basically the lunar program, and then you're going to try and land the ship. So pay attention to a whole bunch of things that I want. So like when you look on number 6, I say, hey, make a free body diagram sketch off to the left. It doesn't have to be an exact drawing to scale. I just want to sketch, but I want the forces and I want the numeric values. Okay? And then the same thing is going to happen on number 9. You're going to make a free body diagram. You're going to make a sketch. Those are the numbers that you've got. Here you go. So, page 1, page 2 for tomorrow. That's all your homework is. So, I'm done. You have the rest of the time.